Hello everyone, we're back for another rousing around of Chapter 4. Now we're on Section 3 in Chapter 4, dealing with logarithmic functions. One thing to remember back from earlier is that exponential functions pass the horizontal line test. So, if you think back to what the basic exponential looks like, as long as b is bigger than 1, it looks a little something like this, where it's flat on one side and then ramps up quickly going the other way. If b is between 0 and 1, we still have that same general shape, except now, sorry about that. Except for now, what it's doing is, instead of going up and to the right, it's going up and to the left, and then it's flattening out as we get closer to the x-axis as we go to the right. But the big thing I want to point out is that these things pass the horizontal line test. They pass the vertical line test and they are functions, but they also pass the horizontal line test, meaning they are one-to-one. Since they are one-to-one, exponential functions have inverses, and that those inverses are logarithmic functions. Okay, so here's the definition. If f of x equals b to the x, then the inverse of x is log base b. So that doesn't say a whole lot, just what I just said. And f inverse is called a logarithmic function with base b. What's important is this statement right here. If you say that y is equal to the log base b of x, that's exactly the same as saying that x is equal to b to the y power. Okay? So that's important to be able to interpret what's going on here. So, in other words, when you see log base b of x, what you need to ask yourself is, what power do I need to put on x, or excuse me, put on b to get x? So y is the power you put on b to get x. Okay? So, if we look at some examples here, what power do you have to put on 3 to get 9? Well, that's 2, because 3 to the 2 power is 9. What power do you have to put on 2 to get 1/4? Well, remember we use negative exponents to flip things, so that's going to be -2. The negative flips it down, and raising 2 to the 2 power gives you 4. What about this one? 64 to what power gives you 8? Well, you have to take the square root of 64 to get 8. So, what that means is we have to take 64 to the 1/2 power to get 8. So what about this one? 5 to what power gives you 1? Well, as long as b is not 0, anything to the 0 power is 1. So, same thing with 17. 17 is not 0, so 17 to the 0 power is 1. With 52, should be no surprise that 52 to the 0 power is 1. So one thing that I should keep in mind is that since these logs are defined as bases to exponentials, inverses to exponentials, we have the same restrictions for logs. For logs, b either has to be bigger than 1 or between 0 and 1. Okay? Okay, moving on. So, this difference between the log form and the exponential form is a big one, because often converting between the forms can help you solve these problems. So, if we look at this first problem, we want to know what is the log base 5 of 25, and that equals x. Well, what the log equals is an exponent, so 5 to the x is equal to 25. 25. So, you probably already see that x is equal to 2, but maybe seeing it in this exponential form is a little bit easier. Same sort of thing with this next one. 6, the base, to the power of x equals 6. So what exponent do you have to put on 6 to get 6? Well, that exponent is 1. Okay? So let's adjust this a little bit. Let's say that the log base 4 of x is -3. So now we have to think about 4 to this gives us that. So what that means is 4 to the -3 power is x. And this one actually looked a little more complicated to start, at least in my opinion, but it's actually pretty easy. You take 4 to the negative 3, and that's 1 over 4 to the third, which is 1 over 64. Okay? So let's look at this next question. The log base b of 1 is what? Is it 0? Is it 1? Is it b itself? Or does it depend on the value of b? Well, I already mentioned the answer to this. It is a. As long as b is not 0, and remember we're eliminating that from consideration, so as long as b is not 0, anything to the 0 power is 1, so no matter what b is, the power you have to put on b to get 1 is 0. So the reason that's important is because just like before we had this point that shows up on every exponential function, the point 0, 1. Well, we have a similar point on log functions. Because the input of 1 always gives us an output of 0, the point 0, 1, 1, 0, sorry. 1, 0 is on every graph of untransformed exponential functions. So if we just look at a few examples, if we look at this original function that I have graphed right here, this exponential, it's y equals 2 to the x. Okay, so if you have x and you have 2 to the x, we can look at a few values. So for example, at where an x is 1, you get 2. So that's right here, that point, or close to it. Negative 2 of an x gives us a fourth. So if we go to negative 2, it's up a little ways, but not very far, at 1/4. And again, my dots are an issue. And if we go to, say, x equals 2, we get 4. That's this point way up here. Okay? So, what if we look at the log now? If we have x, we have the log base 2 of x, and start looking at some similar points, what we're going to see is the behavior of inverse functions that we've noticed before. Remember, if x is 2, that's the log base 2 the log base 2 of 2. So what power do we have to put on 2 to get 2 back? It's 1. So that's the point where x is 2 and y is 1. But notice, that's just these 2 points with the roles of inputs and outputs switched. Here the input's 2, the output's 1. Here the input's 1, the output's 2. Okay? If x is a fourth, well, I think we've already seen, have we not, that the log of, that should be a fourth, not a half. The log base 2 of 1/4 is negative 2, and we switch the roles of inputs and outputs there. But where does that point line up? Where x is 1/4 is right about here. Go down to negative 2. It's right about there. Okay? And finally, the log base 2 of 4 is the exponent you have to put on 2 to get 4, and that is 2. So if you go x equals 4 up to 2, there we have some points. And now if we connect those, we get a graph that looks a little something like this. Okay? So there's our graph. So one thing that we didn't talk about in section 1.5 or 1.6, must have been 1.6 I think, when we were talking about inverse functions, is that the graphs of inverse functions are reflections about this line right here, y equals x. Okay? But you can sort of see that's the case, right? The exponential function here looks like it got flipped over that to land right there. Okay? So if that happens, remember we had a horizontal asymptote way up here because this gets closer and closer. When it gets flipped over, now we get an asymptote as it goes down this way. So the log base 2 of x has a vertical asymptote. and it happens at x equals 0, that vertical line, which is the y-axis. So this is the general basic form of an equation, okay? Or excuse me, a general basic logarithmic function. And we can adjust it from there to graph more complicated ones. So let's look at that. So here we're going to do log base 2 of x minus 1 plus 2. So we have some transformations here. We're adding 2 on the outside, so that makes us go up 2. We're also subtracting 1 on the inside, so that's a horizontal shift, but keep in mind those are generally counterintuitive. So if you subtract, you actually go to the right. So let's put our basic function in there first. So log base 2 of x looks something like that, but we're going to go over 1 and up 2. So again, this is sort of our pivot point, like the point 0, 1 was before. So we're going to move this point to the right 1 and up 2. Don't forget that the vertical asymptote also moves, so that moves to the left. And it looks like this, and so now we can draw in our function. And it looks like this here. Okay? So again, we're keeping the same general shape, we're just applying transformations as necessary. So again, our basic function looks like this. Then we have to decide for ourselves, what is the transformation we have happening here? So since we're multiplying by -1 on the outside, I can already hear you telling yourself that that means we reflect it over the x-axis. All these positive y's, since we're multiplying on the outside, the outputs become negative. So the positive y's become negative, and the negative y's become positive. So it's just reflected along the x-axis. Still goes through this point, but flattens out that way. Alright? And so there's our shape. Hopefully you can draw it more nicely than I can. Alright? So let's get into some properties of logs. So the first property we're going to look at is this one. It's one we've already seen. B to the 0 power is 1, so the log base b of 1 is 0. Over here, we can put this into the exponential form if we like. But what power do we have to put on b to get b? The answer to that is 1. These aren't quite as straightforward, but if you think about it, there's a couple ways to approach it. One is to say that what power do we have to put on b to get b to the x power? And it turns out the power we have to put on b is just x. Okay? So we can think of this way. The log base 5 of 25, well, we can rewrite 25 as 5 squared. So what power do we have to put on 5 to get 5 squared? That power is 2. Okay? The other way you can think about this original equation here is to say that we're going to use the inverse properties of logs and exponents. Here we're composing functions, right? We're taking the function b to the x power and plugging it into the logs. But anytime you compose inverse functions, what you get left with is just x. So that still applies when we're doing this here, because here again we're composing inverse functions, and anytime you compose inverse functions you just get x. Okay? So we can do the same sort of thing right here. If we have we have 5 as a base for an exponential and 5 as a base for a log. If you compose those two, what you get is what you put in to begin with. In this case, it is 10. Okay? So those are some properties of logs. Some more down here are actually going to be more useful. This first one just highlights the fact for us that logs, the log base b of x is 1 to 1. Let me try writing is one more time. Much better. 1 to 1. So the log passes the log graph passes the horizontal line test, so it's 1 to 1. These last three are more interesting, so we'll use those more in the next slide. But what it says is that if you have the product inside, you add outside. So take note of that. Product inside add or sum on the outside. Okay? Same sort of rule here, except now we're talking about a product, or excuse me, a quotient inside, we subtract outside. So if you divide inside in, you subtract out. And so when I say outside, I just mean the outside of the exponential. Okay? So we can go both directions, and we will. So we can take something like this and expand it out, or we can take something like that and compress it down like so. Okay? The last property just has to deal with exponents inside. If you have an exponent on the inside, you can pull it out front like so. Okay? So some other common logs you might see are the log and the ln. So those are what's called the common log, and this is the natural log. So these are just logs that come up a lot as in science and biology, that sort of thing. So chemistry. Here, when you just see log, that's shorthand for log base 10. If you see ln, the natural log, that's shorthand for log base e. As you saw in 4.2, exponential functions with base e show up a lot, so their logs show up just as much. Okay, so just keep that sort of in your back pocket for now. We'll come back to it. So let's go back to using those properties that we talked about. We're going to do some expanding and contracting, I suppose, of logs. So let's look at this. So we have the log base 10 of this quotient. So the first thing I'm going to do is use property 7 here, because I have a quotient on the inside of a log. So if I'm going to do that, I'm going to rewrite that as the log of the numerator minus the log of the denominator. Okay, so I'm not done yet. I want to keep breaking this down until I have a log of a single number or a single variable with no exponents anywhere. So I kind of have that right here. I don't have that here because now I still have a product there. So I'm going to break that up as well. Log of 2 plus the log of x to the third minus the log of y. And there's one more step right here, because we have an exponent. We can use that last property to pull that exponent down front. So the log of 2 comes along plus 3 now of the log of x minus the log of y. Okay, so so there it is. It's expanded out as much as we can get it. We're taking the log of a single term inside there, and any exponents have been pulled out. Okay, let's do the same sort of thing here, except for now we notice that there's nothing that tells us what to do with radicals. Luckily, it doesn't have to, because radicals can be rewritten as exponents. So let's do that first. So next, we have a couple options. We can use the third property to bring this exponent way out front, or we can bring this exponent in and distribute it. So I recommend doing that. And you would see why if you did it the other way. It's not wrong, you get the right answer, but it's just easier to do it this way. So the new exponent on x is 1/2 times 2, which is just 1. The new exponent on y is 3 times 1/2, which is 3/2. Okay? So again, we need to keep going. We don't have this completely separated out. So that's the natural log of x plus the natural log of y to the 3/2. And then the last thing we have to do then is bring this 3/2 out front. So that is equal to the natural log of x plus 3/2 times the natural log of y. Okay? So That's what you do when you're expanding. When we're rewriting things as a single log, it's a similar sort of thing. We identify which properties can be used where. So now one thing I want to point out here is we see a subtraction, but we can't use this second property quite yet. And the reason we can't is because this only applies when you have a log minus another log. It doesn't actually say anything when you have something times a log minus something times a log. But that's okay. We can rewrite this as the difference of two logs by simply bringing that exponent up top. So instead of having 3 times the natural log of x, we have the natural log of x to the third. And instead of 2 times the natural log of y, we have the natural log of y squared. So now at this point we have a difference. So don't copy this next bit. Here's a really common mistake. People see subtraction and they know a quotient is coming, so they do this. Okay, so that's wrong, because here the difference of two quotients, or excuse me, the difference of when you take a natural log of something minus the natural log of something, that's not the same as the natural log of that thing divided by the second one. What we do instead, and this part you can copy, the quotient appears on the inside of the natural log. Okay, so hopefully everybody can see the difference there, because one way is right and the other way is a very common mistake that is easy to make. Okay, so again, when you see the difference of quotients on the difference of logs on the outside, that means the quotient on the inside, not quotient on the outside. Okay, so finally here we have 3 terms. So when you have 3 terms, there's none of our properties deal with 3 terms, but we can still handle this sort of 2 at a time. So let's deal with these first 2 first. We have one log minus another, so that becomes the log of x over y, and then we have the minus log z sort of coming along. Okay, so now again we have to do a quotient of the inputs, so that's the log of x over y log of x, let me try that one more time. The log of x over y all over z. Log of that mess. Okay? Well, if you do some simplifying here, we have a fraction divided by z. You can treat that as z over 1. Divide by fractions, you reciprocate and multiply. What you're going to see is where we end up is the log of x over y times z. Okay, so so if you kind of look back at this original problem and see where we end up, what you might realize is that the log of x was positive. X ended up in the numerator. Log of y was negative. Y was down on the bottom. Log of z was negative. Z is on the bottom. And that's going to hold true. So as you get more practice with this, maybe you'll recognize things like that and maybe be able to cut to the chase here a little bit quicker. Okay? So let's look at this last question here. If the log of x is negative 1, the log of y is 7, what is the log of xy? Well, it might seem like it's kind of hard to tell because we know what log x is, we know what log y is, we don't know anything about x times y. Okay, we don't know anything about what x is or what y is, so we don't know what x times y is. But we can use our property to say that this is the log of x plus the log of y. And we know that the log of x is negative 1, and we know that the log of y is 7, so overall what we're left with is 6. Okay? So next up then is learning how to deal with these in your calculator. So this is fairly straightforward. We have LOG button on our calculators. We have LN button on our calculators, so we can use those. If you put this in your calculator, you're going to get a rather long decimal. But if you do some rounding, you're going to see it's 4.13. Okay, so that should make a little bit of sense. 10 to the 4th is 10,000. 10 to the 5th is 100,000, and 13,000 is a lot closer to 10,000. So the answer is closer to 4 than it is 5. And we can check that. 10 to the 4.13. So remember, there's a whole lot of decimals there, and I did some rounding. So what that means is this isn't going to be exact, but it's not too far off. Okay, so you can see this is about 33 away, these two numbers, and when you're talking about things in the range of 13,400, 33 isn't so big. Okay, so what about this one? We can do the same sort of thing. Take the natural log of 92.13. The calculator is going to tell us it's 4.52, and so we can take, to check that, e to the 4.52 power. And again, it's not exact, but it's sufficiently close. The more decimals you have here, if you would have did 4 decimal places instead of 2, this would be closer. Okay, so if you look really hard, you're not going to find anything besides log and natural log. Okay, but that doesn't mean all hope is lost when you're calculating things like this down here. So here we don't have log base 5 on our calculator. However, we have this handy-dandy change of base formula. So what that allows us to do is take something, a log that's base 5, for example, and use the buttons we do have, log, log, and natural log. So this is the way it works. You just take the log of the input divided by the log of the base, and you can do that with a common log, or you can do that with the natural log. So if we do that, let me just do the natural log first, just for fun. So we have the natural log of 32 divided by the natural log of 5. If we do those individually, it's 3 point, remember there's a decimal there, 3.466 over 1.609. Okay? So if you do that division, then you get 2.15. Okay? And again, there's nothing special about the natural log there. I could have used the common log. So this is what it looks like if you do that. We're going to take the log of the input into the log function divided by the log of 7. So here, if I do that, I get 2.326. That dash is a decimal, not a comma, over 0.845. Okay? Again, we do that subtraction, or that division, we get 2.753. Okay? And again, we should probably check that, but if we do 7 to the power of 2.753, we see that we get 212.11. And again, it's not perfect, but it's pretty darn close. Okay, so that's the introduction to logs. In the next section, we'll look at some logarithmic models, and that will be it for Chapter 4. Hope you've learned a lot.